Welcome back, everybody. So in this video, we'll be examining various mathematical models that relate to first order differential equations. We'll be looking at stirred tank equations and then most commonly population models. Let's get started. The formulation of a stirred tank equation is that x of t would be a function that indicates the amount. It could be a dissolvent, um, dissolvent. It could be like salt or sugar or what have you. This could be the amount of salt or sugar in water or some other fluid. And it's in a tank here that is mixed in with uh, with the salt or some other dissolvent, right? So, and the formulation of this differential equation is the rate of change of the amount of salt or the amount of salt or sugar in the fluid or in the tank, right? So all it is that dx, so dx dt, this will equal to the rate of the fluid that's going into the tank minus the rate that's going out of the tank, right? So the output rate. Rate in, so the input, and the rate out is just your output, right? So before we get into sort of the terminal, an example of the stirred tank um, differential equation. We should go over some definitions here. So in chemistry, okay, so these stirred tank equations are most common in the field of chemistry. Um, so we'll have a solute. So solute is a dissolvable substance, or a dissolvent, right? So it could be salt or sugar. These are just examples. You'll have what is called a solvent, right? So a solvent is it's a solute mixed in with another substance. So this could be water or brine or some other type of fluid, right? Some other type of it typically is a liquid, right? And then you'll have what's called the concentration. The concentration. This is actually a formula in chemistry. So it equals to the mass of the solute per volume of the solution. Okay. Solution beating a solution being the combination of the solute plus the solvent, right? Okay, so that's the solution here, right? So that's in chemistry. So what's going to be the challenge here to form a stirred tank differential equation is to examine the the rate of the solvent, right? The solvent rate that's coming in, along with the volume of the liquid that's coming into the tank, right? And then the output rate is you're going to look at the solvent rate that goes out of the tank. So this is in, and then this here is out. And then you want to multiply that by the rate of the water or the liquid that's coming out, right? So that's the challenge. Okay, so in other words, right, we are looking at how the amount of salt changes um, um, uh, when fluid is coming into the tank and then out of the tank simultaneously, right? So these events are occurring simultaneously here. So we have to multiply those quantities together, right? The rate that's coming in and the rate that's going out. Well, it's we're eliminating that substance. So what is the solution that we are eliminating? Well, it's the solvent, right? The solvent, and then the rate of the liquid that's going out of the tank simultaneously. So we have to multiply those other quantities together as well, right? So let me write this out clearly. Let me do a larger eraser. So hopefully you wrote those definitions down. So, Jesus. Okay. Okay, come on, please. So the formulation of the differential equation of a stirred tank, right? Well, really, it's just the solvent rate that's coming in times the volume of the liquid minus or I should say the concentration here because it's mixing in with the solvent, the salt, and then the water. So it's so really I should write out the concentration. Let me redo this. Yeah, so essentially, oh, I forgot that part there. So let me erase that. So essentially, dx dt is the input rate minus the output rate, and then in particular, this should be the concentration of the liquid that's going in times the rate of the water that's going in minus the concentration going out of the tank. times the rate of the water that it is going out of the tank, right? Okay. And so let me write out the units here. So this should be, so this is grams per liter, and this is liters per minute, right? Typically. And this is grams per liter here, and then this is liters per minute. So you should have a differential equation with respect to time, right? So that's essentially what a stirred tank differential equation represents, right? So I think that's it. So here's an example. So if we have a brine solution of salt that flows at a constant rate of 8 liters per minute, so into a large tank. So if I have a tank here, and there's the outflow pipe here, and let me erase that. And okay, so here's my tank. So here's my tank, right? And it's filled with brine, and salt flows into the tank at a constant rate of 8 liters per minute, right? We know that this tank is filled with 100 liters of water, so the volume of this tank is 100 liters. And the solute, which is the salt in this case, it's going into the tank at 0.5. Oh, that's the initial amount of salt. So the initial amount of salt in the tank is 0.5 kilograms, right? So A of T in this case is the amount of salt in the solution, right? So in kilograms, all right? So the solution that's inside the tank is stirred and it flows out of the tank at the same rate as the rate of the water that's going into the tank. So we're going to go have an outflow rate of 8 liters per minute of the solvent, right, of the solution. And we already know that the solvent rate, okay, I should say the concentration rate is 0.05 kilograms per liter, right? So the concentration that's going in, it's the amount of the substance in the solution per volume of liquid. So the concentration is at 0.05 kilograms per liter. So we want to determine the mass of the salt in the tank after T minutes, okay? And we want to figure out when will the concentration of salt reach 0.02 kilograms per liter. Okay. So, all right. All right. So A is the amount of salt in the solution. So that means dA dt. This would equal to the concentration of the fluid going in minus times the rate of the water that's going in minus the concentration that's going out times the rate of the water that's going out of the tank. Okay. All right. So now dA dt, the concentration that's going into the tank is 0.05 kilograms per liter. The rate of the water that's going in, well, that's 8 liters per minute, right? Minus the concentration that's going out, well, that's the same as the rate of the concentration that's coming in. All right, so that's the rate of the water. So the rate of the water we know, right? So the rate of the water, that is 8 liters per minute. And now the challenge is we want to figure out the concentration of the fluid that's going out. We know that the volume of the water is 100 liters. So that means, so A of T is the amount of salt in the solution. So the concentration in this case, it's just A of T over the volume of the tank, which is 100, not 1,000. So this is the formulation of the stirred tank differential equation. Okay? Right? So we have so dA dt is equal to 0.4 and then minus 0.08 times A of T. Okay? This here is a linear differential equation, right? So now, so we'll have A prime of T, that's dA dt. Oops, let me erase this. So I have dA dt plus 0.08 times A of T equals to 0.4, right? This here is a linear differential equation, so we're going to have to use the integrating factor. So in this case, it's 0e to the 0.08 times t. And if I multiply both sides of this equation here by I, I'll get that, so I will get this equation, d dt of A of T times e to the 0.08 times t equals 0.4 e to the 0.08 t. Okay? Then if we integrate both sides, we'll have that A of T times e to the 0.08 times t equals 2. So if I integrate on the right-hand side, I will get 5 times e to the 0.08 t plus c. Okay? And so I'll have A of T equals to 5 plus c times e to the minus 0.08 times t. Okay? All right. So now, we know the initial amount of salt is 0.05, right? And so I'm going to write this over on the upper left-hand corner. So we know that A of 0 is 5. I'm sorry, 0.5. So that means when it's 0, we will have 5. So that's 0. So plus C equals 0.5. And so C is equal to minus 4.5. And so therefore, the particular solution would be 5 minus 4.5 times e to the minus 0.08 times t. Okay? 0.08 times T. Okay. And all right, so all right, so right. Okay. So that's part A, I guess. So basically, to figure out part B, when will the concentration of salt in the tank reach 0.02 kilograms per liter? So that's essentially saying, right? So if this is the concentration, we want to look at the amount of salt. A of T is the amount of salt at that time. So basically, what we want to do is so if I erase, so since A of T is the amount of the salt in the tank, all we have to do is 0.02 kilograms per liter. All we have to do is just multiply this by the volume, and you'll get the amount of the salt in the tank at that time. So in this case, it's 2 kilograms. So we want to look at what is the time where we will have 2 kilograms of salt in the tank. So essentially, we take our particular solution and we just solve for T, right? All right, so let's just solve for T in this equation, minus 4.5 4.5 e to the minus 0.08 t equals 2. And then just solve for t here, right? That shouldn't be too difficult. And then you should get about that t is approximately 5.07 minutes. Okay, if you do this right. All right, so that's just an example of a stirred tank. It's a differential equation problem. Okay, so the most common model that you'll see in first order differential equations is a population model. Okay, so P of T will denote the population of a species or an organism, or could at time T, right? So T could be years or hours or minutes, what have you, right? So there's going to be two types. We will deal with population growth. So you may have seen this in the past with, let's say, continuous compound interest, right? Right, continuous compound interest, or looking at growth of bacteria, right? Growth of bacteria, and then so that indicates population growth, and then you'll have what's called population decay. And it all really depends on this constant K. If it's greater than 0, you're dealing with population growth. And if it's less than 0, it's population decay, right? Population decay usually is dealt with carbon dating, determining the age of an artifact by looking at the isotope of carbon inside of an artifact, or bones, right? So you can use population decay equations to look at uh, uh, the age of an artifact, right? Using that. You'll deal with the radioactivity, right? Radioactive materials, right? Just looking at, for example, uranium-238. Okay. And then, because in our real world, there's a population can't grow exponentially, right? There's limited resources, right? And a population needs food to survive, right? So you'll deal with another type of equation called logistic growth. Logistic growth is one of my favorites. And the differential equation looks like this, right? R is what's called the population growth rate. And then we want to formulate an equation so the population doesn't increase, right? It sort of limits out as time moves forward, right? And so that's what this K constant represents. So K represents what's called the carrying capacity. The carrying capacity, right? So it's just like the stopping point, right? And when a population will die off. Okay. So those are the two different types of population growth models, or decay models for that matter. So I want to look at how we would formulate a general solution for the exponential and the logarithm equation. So let's just take, for example, the exponential equation, right? Let me label out R instead of K. Now that would be different much later. Okay, so R times P. Well, it turns out this is a separable differential equation, right? So if we gather all of the P variables to one side and all the T variables to the other side, we'll have dP over P equals to R times dt, right? Times dt. Then if we integrate both sides, we'll have the natural log of the absolute value of P equals to R times T plus C, right? So if we take the exponential of both sides, we'll have P of T equals to e to the RT plus C. But e to the C is just another constant, so we'll just write this out as big C e to the RT, right? So a general solution for an exponential equation is C times e to the RT, right? And then typically, an initial population is denoted like this. So this is what's called the initial population. The initial population. Okay, so the initial population. And so the particular solution for an exponential equation like this, well, it's just P0 e to the RT. E to the RT. And that's it. Okay, so for a population growth function, you'll deal with what's called the doubling time. Essentially, the time it takes for a population to double in size. So really, you're going to solve where t is equal to, so you want to solve for t or r such that the population would double. So t times p0, p0 is the initial population, times e to the RT. You still have e to the RT equals to 2. And so if I take the natural log of both sides, I'll have r times t equals to ln of 2, right? And this is what's called the doubling time here. Okay. And then also you'll have for exponential decay, the half-life. Half-life just means the time it takes for half of the amount of the substance to be eliminated, right? So essentially it's just the same thing, but except you have 1/2 over R. So that's the half-life. Okay. So these are key to solving for the growth rate or the decay rate, respectively. So yeah, so that is the formulation for exponential growth or exponential decay. All right. And what's really going to be exciting is the logistic equation. So I want to talk about that for a bit. So algebraically, I want to talk about figuring out the general solution, in particular solution of the logistic differential equation. The logistic differential equation. Okay. R times P times 1 minus P over K. All right. So it's typically written out like this. There's many formulations. I'll go over the formulations of a logistic differential equation, but this here is the most common, right? The most common formulation. So it turns out this is also a separable differential equation, right? So if we gather all of the p variables on the left-hand side, I'll have dp over p times 1 minus p over k. And this equals to r times dt, right? And if I integrate both sides, the right-hand side, it's pretty easy. It's just r times t plus just a constant, right? But this left-hand side, we're gonna have to use partial fractions decomposition, right? So we'll have 1 over p times 1 minus p over k dp, right? And then by partial fractions, right? So this would equal to a over p plus b over 1 minus p over k. And so from here, we'll have 1 is equal to a times 1 minus p over k plus b times p, right? And we're going to solve for capital A and B, and capital A and capital B. So if p is 0, we will have, so if p is 0, the A is 1. And if p is k, right? B is equal to 1 over k. B is equal to 1 over k. And so that means we'll have this integral. Oh, shoot. This integral. One over k is a constant. So this is that dp. One minus p over k. And okay. It's probably best if I multiply the numerator and the denominator here by k. I don't want to deal with fractions. So let's see if that works. So from there, I'll have K over P times K minus P. B over K minus P. And erase that. Okay. So, all right, that would make things a lot simpler. Times K minus P plus B times P. And if P is 0, I'll have A is 1. And then if P is K, B is 1. Yeah, so I'll have that. And so this integral here would equal to this integral. So 1 over P plus 1 over K minus P dP. Okay. And so this equals to the natural log of the absolute value of P minus the natural log of the absolute value of K minus P. Okay, K minus P. And so I can collapse this into one single logarithm, right, by properties of logarithms. So essentially this left-hand side will become this quantity minus P equals RT plus C. And if I take the exponential to both sides, I'll have, so P over K minus P is equal to another constant times e to the RT, right? Times e to the RT. And now from here, we just solve for P, right? So we solve for P. So what is that going to look like? Well, let's see. So we'll have that P is equal to C times e to the RT times K minus P. And then we'll have P plus P times C times e to the RT equals to K times C e to the RT. And then factor out P on the left-hand side. So this would be 1 plus C times e to the RT equals to K times C e to the RT. And so therefore, P, this is a function in T, this would equal to K times C e to the RT divided by 1 plus C times e to the RT. So this right here, folks, is the general solution for a logistic differential equation, right? General solution. Okay. Now, if we assume that the initial condition of P at time 0 is equal to P naught, right? P naught is just an arbitrary constant. Well, if T is 0, well, we'll have we will have K in the numerator, and then we'll have 1 plus C, which equals to P0. And then from here, this is going to solve for C. Solve for C, right? And so, okay. So we'll have K is equal to P0 times 1 plus C. Right, so we'll have K is equal to P0 plus C times P0. And then we'll have C times P0 is equal to K minus P0. Right? And then, so C is equal to K minus P0 over P0. Let's see. Yeah. Okay. So that's C. So that's a figure out C in the logistic differential equation, right? And then, yeah. So that is essentially the background behind the logistic differential equation. So let's see. Oh, K times C. All right. I see the mistake. All right, hold on 1 second. Okay, can I erase this? Okay. So this is P is 0 and yeah. There we go. And then C would equal to P0 divided by K minus P0. That's the constant I'm looking for. Okay, there we go. So this here's how you figure out what C is, right? The constant. And um and then essentially another way is if we multiply the yeah, if we multiply the numerator and denominator by the logistic equation by e to the minus RT, right? This is just another way. So K times C over that is E raised to the minus RT plus C, right? And another way to solve for the K constant, well, just look at as T approaches infinity, right? So if T approaches infinity, this quantity right here, oh, Jesus. So this quantity right here, this will be 0. And so this will approach to K, right? This will approach to K. Yeah, so that will approach the carrying capacity. Okay. And then the other thing I want to mention is the slope field, right? The slope field of the logistic differential equation. Okay. Because the differential equation only is dependent on the population itself, right? Okay. So we're going to have points that are equilibrium, right? Where dp dt equals 0, right? And that's where P is 0 or P equals K. Right? So then on a slope field, right? So we're going to have equilibrium points at P equals 0 and then at P equals K. So we're going to have horizontal lines here at P equals 0 and then at P equals K. Right? So if I'm dealing with the key TP axis here. So if excuse me, so if P is negative, that's when the population will die off. So if P is negative, well, obviously this quantity would be negative, but this would be positive. So this would be a negative quantity. So eventually you'll have hash marks that are getting more and more negative as the population decreases, so it will die off, right? But what's interesting here is that in this range here, if P is in between 0 and K, so what that means is, okay, so where is the other marker? Okay, so we'll have one solution curve like this, right? It will approach 0 this way. And if P is greater than 0 and less than K, so let's say P equals 1, right? So this would be a positive quantity, and also this would still be positive. So we're going to have positive hash marks here. And then it's going to get more positive. And as we get closer to P equals K, your hash marks will flatten out. So you'll flatten out here. And so what you'll produce as a solution curve would be something like this, right? What's called a sigmoid curve, right? So a little S shape. And if P is greater than K, well, that's pretty obvious what's going to happen. So if P is greater than 0, I'm sorry, P is greater than K, this would be positive, and then this would be a negative quantity. And so your slopes will, so your slopes would be negative here. And it will become more and more negative. And so we're having a solution curve like this, let's say, right? So, and you'll have also what's called a phase diagram, right? So 0 and then K for P prime of T. And so you can point out the direction of the slopes like this. So it's unstable at 0 and it's stable at K, since this arrow right here and this arrow right here will approach to K. So that's another point I want to mention. So if you have your slope, you have your solution curves approaching to an equilibrium value, you'll have what's called a stable point. And if at P equals 0 in this case, the solution curves are they're going away from equilibrium, right? As time increases, so it's unstable. Okay, so it's unstable. So that's a little bit about the logistic differential equation. Okay, so let's look at an example on using these such equations. All right, so the most common use for exponential growth or decay differential equations, well, it deals with carbon dating. So carbon dating is often used to determine the age of a fossil or bones or what have you, right? So for example, a skull was found in a cave in South Africa, along with the remains of a campfire. Archaeologists believe the age of the skull to be the same age as the campfire. It is determined that only 2% of the original amount of carbon-14 remains in the burnt wood of the campfire. Estimate the age of the skull if the half-life of carbon-14 is about 5,600 years. Okay, so I want you to pause the video and formulate a differential equation in this problem, and then try to determine the age of the skull. So best luck to you. All right, so now we want to look at how to formulate this differential equation of carbon-14, right? So an exponential differential equation looks like this, right? The derivative of the function is equal to K times P of T, right? So we know that the general solution looks like this, right? And since we're dealing with carbon dating, the K variable is less than 0, right? So we want a decay rate, right? So what we now know is that the half-life of carbon-14 is 5,600 years. So we're going to use that to solve for K, right? Yeah, we're going to use that to solve for K. So, okay. So we want to solve for the decay rate. So that means we're going to have the natural log of 1/2 over T equals K, right? Right, so that is the K constant, right? So it's at 0.00012, or yeah, or negative, I should say. Natural log of 1/2, and it's negative. So negative 0.0000123, I guess. But I'm going to write this out in its exact fractional form like that. So now we know also that 2% of the original amount of carbon-14 remains in the burnt wood of the campfire. So that means, so we know that 0.02 times P0, well, that has to equal to P0 times e to the KT, right? And so that means 0.02 equals to e to the KT. We already know that K is equal to this quantity. So all we have to do is solve for T. T is the age of the artifact, and that is what we would get. So T is, so if we take the natural log of both sides, right, we'll have, so we'll have ln of 0.02 equals to KT. And so T is equal to natural log of 0.02 over K. And so T is equal to natural log of 0.02 over natural log of 0.5 over 5,600, right? So that is approximately 31,605.59 years old. Okay, so pretty amazing, right? So here's another example. Okay, and I want you to try this out on your own, but in 1990, the Department of Natural Resources released 1,000 splake, so it's a crossbreed of a fish, into a lake, right? So in 1997, the population of splake in the lake was estimated to be 3,000, right? So they called the exponential growth equation the Malthusian law. So just use the exponential growth or decay equation. Right? So in this case, you're going to use that for population growth. And then estimate the population splake in the lake in the year 2020, right? Okay. And if you do this right, I'm not going to do this example, but it's the same process as you do in the previous example. You should get the general solution as 1,000 e to the RT. Okay. R is equal to the natural log of 3 over 7. Right, you should get this right. And then the population at 30 years, so that's a span between So this is the population in 2020. This would be about 110,867.99 fish. At least it's 8 fish, right? So that's what you should get. Okay, but I want to move over to the logistic equation example. Right, so let me erase this. Okay, so in this previous problem, right, so this time, what you want to do is, suppose we have this additional information that the population of the splake now in 2004 was 5,000. And then you're gonna use a logistic model to estimate the population of the splake in 2020. Okay, and then you're gonna use the formulating formulas in the problem 12 in the textbook. So this is just another way to express a logistic differential equation, right? P0 and P1 are different populations. Okay. All right, so this is another way to formulate, so this is another way. So this is another expression for the logistic equation, logistic differential equation, right? So this is another expression for the logistic equation, right? And then to determine the A and the P1 in this case, you're going to use these formulas, okay? So P1, this would equal to PA times PV minus 2 times P0 times PB plus P0 times PA divided by PA squared minus P0 times PB, all that times by PA. And then the capital A quantity, this would equal to 1 over P1 times T sub A times the natural log of PB minus PA minus P0 divided by P0 minus PB minus PA. How that comes about is so if you're given 3 points, PA and then TB, PB, you want to formulate the logistic function, right? So you're going to use those 3 points to determine a logistic function that passes through those 3 points, right? Right, so this is a general solution for a logistic differential equation. So the way where these formulas come about, well, it's just it's equivalent to formulating a logistic function that passes through these 3 points. Okay, T0, P0, that's pretty straightforward, right? Um, so you're going to use that to solve for the C constant, right? C is the C was P0 minus K minus P0, right? We already know that. But the hard part is solving for the carrying capacity and the growth rate. And you're going to use the last 2 points to solve for those quantities. But nevertheless, you'll get these formulations, right, in your logistic functions. So, okay, can I erase this, please? All right. So, but the straightforward process here is just figuring out is to compute the P0, PA, and then the PB quantities, right? So we know that P0 is 1000, right? And we know that in 1997 there was a spike in 3000, so that means P7 is 3000. And we know that in 2004, that's a span of 14 years since 1990, and that would equal to 5,000. So essentially this here is P0, this is PA, this here is PB. Okay, so, and then T0 is 0, and then TA is 7, and then TB is 14. Okay. So essentially just plug in the numbers, right? So 3,000 times 5,000 minus 2 times 1,000 times 5,000 plus 1,000 times 3,000 over 3,000 squared minus 1,000 times 5,000 times 3,000. Okay. And then A is equal to 1 over P1, this quantity right here, times T sub A, which is 7, times the natural log of 5,000. 3,000 minus 1,000 over 1,000 times 5,000 minus 3,000. Okay. And then just write out the particular solution, right? So it's just P0 times P1 over P0 plus P1 minus P0 times e to the minus a P1 times t. That's a fraction. All right, so that's it. Okay, so pretty straightforward. And then here's some problems for you to check comprehension, right? Let's see. There's also going to be Newton's law of cooling, right? Newton's law of cooling. I haven't talked about that yet, but this is how you would find Newton's law of cooling. And I will talk about this different type of model to examine the temperature of objects. Newton's law of cooling. Okay. So stick around for that. But we are going to move forward with once we're done with first order math models like these, we are going to move on to chapter 4 in the textbook, which deals with second order differential equations. All right, so that's going to be really exciting. So stay tuned for that. Please give a like. If you have questions, let me know. But otherwise, I'll see you next time. Take care.